In this video, I'm going to present an example for a mixed factorial ANOVA. Remember, to be a factorial ANOVA, you need to have two or more independent variables, and to be mixed, you have one of those independent variables as independent groups, the other independent variable as repeated measures. In the example I'm going to show here, the dependent variable is knowledge of research methods, so something I might do in my research methods course. And my first independent variable is going to be, did you experience research methods when you were an undergrad? That usually does change where you come into the course if you've already been exposed to research methods course already. So did you get it is one option, or you didn't take undergraduate research methods. The other independent variable is knowledge of research methods over time. So I'm going to test it a baseline measure when they come into the class, midterms, and the final exam. The structure of the hypotheses is really similar to what we've done for all other factorial ANOVAs. We're still going to have an interaction hypothesis, which is going to be our main one, and since we're doing null hypothesis testing, we'll start off with the basic of no significant interaction will exist between testing period and whether or not they took undergraduate methods. Then we have our two backup main effects hypotheses. So no significant mean difference will exist in research test scores across the three different time periods, and no significant difference will exist between those who took methods and those who didn't take methods as an undergraduate student. That'll lead us to testing three different F ratios. Now, when I make my substantive hypothesis, I'm going to use this interaction chart as a way to start me. So when I have my interaction chart, maybe I'm assuming that those who are coming in at pretest, if they took methods, maybe they remember a little over 50%. Maybe we're talking about 55% of what they remember, where if you've never had it, maybe you've been exposed to some very basic concept in research but never had a class, maybe you know about 25% to 30% of the course material. At midterm, we're going to see that those who didn't take it are going to try to catch up here because now they've been exposed to half of the semester. So they are gaining material, but maybe haven't fully caught up to those who've taken it. So at that point, maybe we say they're about the same. Maybe we say that those who are those who take it still have a bit of an advantage. But then I'm hoping by the end of the semester, everybody's on an equal playing field. When you set up your SPSS data, it has to look like a combination of doing independent groups and a mixed factorial. So your independent groups variable will need a single column, ones for those who took methods, ones for those who didn't, and then you need one column for each level of the repeated measures variable, so pretest, midterm exam, post-test, and I have the dependent variable is populated within that column. When I look at partitioning the variance, again, like all other things, it's just going to be a combination of what we've seen so far this semester. So the between measures factor, which is my independent groups variable, whether they took methods, that's going to be a between groups variance component, and we'll find that under the between subjects table in SPSS. Then time, because it's repeated measures, is a within subjects factor. It's still explained. The one part that might be a little bit surprising is where the interaction goes. Since the interaction is a combination of repeated measures and independent groups, it's always going to fall, or anytime you have a combo or a mixed component, it's always going to fall under within subjects error. And then error will still be under, there will be error in there. There's also going to be some between subjects error and used to make that between subjects F ratio. So to test homogeneity of variance, we are going to test it again now. We have to do Mauchly's for the repeated measures factor. So you see time is going to be tested using Mauchly's, and we've met that assumption. We also have to do Levine's for the independent groups factor. And notice that we're going to do it across the 3 time points. So we're going to check at Levine's at pretest across the 2 groups, Levine's at mid-test across the 2 groups, and post-test across the 2 groups. So when you're doing homogeneity of variance in mixed factorial ANOVA, unless it's a 2x2, in which case you only do Levine's, and you wouldn't have to do Mauchly's because of the 2 repeated measures component, you're not going to have, or you have to look at both if it's a 3x2 or anything else. So if I do that, since I met the assumption, we're going to take a look at the F table. The F table is going to be a combination of tables. We're going to have to look at the test of within subjects to find the F ratio for time, my repeated measures factor, and the interaction, because we said that the explained portion was going to be partitioned in the within subjects components. For for my independent groups variable research, I'm going to look down here in the between subjects on this research line. So these are my 3 lines that I'm going to have to read to get to my F variable. So we start with the interaction. As always, I have a significant interaction, so I'm going to do a simple effects test. If my interaction hadn't been significant, I could do a Bonferroni or a Fisher's for time for that post hoc. Research was non-significant with a p-value of 0.051, but if it had been significant because it's 2 groups, I would have just compared the means. I've provided you, on Moodle I put the actual syntax there for you, but here's also the syntax that you can use for running a simple effects test, putting in the variable names, making sure you get the different levels of the repeated measures, and there's the independent groups variable, time, polynomial, I have the different tables I want, making sure all the variables match up correctly. And then here is my simple effects output, and we have a couple of different things because we have a mixed factorial. So here's that univariate test. It looks just like what we had in the repeated measure or independent groups factorial lecture, where at time 1, so my baseline measure, I have a significant difference between my 2 groups, and I'd look at the means to figure out who had higher knowledge. Not surprisingly, if I look over here, if I pull this over, I can see that those who took research methods had an average of 55, those who didn't have an average of 30. So it's not totally surprising there that there's a significant difference between the groups. Then if I look at time 2, no significant difference between the 2 groups. Well, also not surprising over here because their scores were 78 and 74.8. So they pretty much caught up to each other. And then for my last one, no significant difference at time 3. And again, our means are pretty close. 88.8, 87.4, really not surprising that they're not significantly different. And here we can see the differential outcome that's driving the statistical significance. So I have a mean difference at time 1, and I have no significant difference at time 2 and 3. The other way to look at that is the pairwise comparison. So if I took the pairwise comparison, I see at time 1, compare those who took methods to those who didn't, and I have that difference. See how the alpha or p-value is the same as the p-value up here? We're just getting this in terms of a t-test because I have mean difference divided by standard error, and whenever I do mean difference over standard error, what I'm getting is a t-statistic. I can also look at that time 2 and time 3, no mean difference, no significant mean difference at time 2, no significant mean difference at time 3. I'd use that to write my statement of the findings. So prior to enrolling in research methods class, grad students took research methods as undergraduate students scored significantly higher in the knowledge of research than those who did not take methods as undergraduate students, but at mid-semester and after completing the course, no significant differences were found between those who took the course and those who didn't. Just to show you what would happen if we were to extend this example into a 2 by 2 by 3. So bring in another factor. Maybe the other factor, really actually I have a typo here. 2 by 2 by 3. So here I have 2, did they take research as undergrad or not? 2, what kind of testing method or teaching method did they use? So let's say we do face-to-face compared to an online class. And then 3, pre, mid, and post. So we're still going to have the 3 main effects now, because we've added a third independent variable of testing period, a teaching method, which is an independent groups variable. Now we have 4 interactions to test. We have an A-B interaction, research by teaching method, an A-C interaction, research by teaching period, an B-C interaction, teaching by testing period, and an A-B-C interaction which is research by testing or teaching method by testing period. And if I were to write out the order of importance, I would test the ABC interaction first. I would look at the other first order interactions next. So this is called a second order interaction. These 3 are called first order interactions. And then we have 3 main effects would be last. So that's the order of importance. And we can see how that plays out in the variance. Now you're starting to really partition that variance really picky, because you have the teaching methods, which is between groups, the independent or the undergraduate methods courses between groups, testing period is research or within groups, and then you have to partition the different interactions. Remember, anytime that you have an interaction that has factor C or time, it's all going to be within groups. And that's it for factorial ANOVAs.